So welcome everybody to the second day of the summer school. So today we have with us Nikolai Matni and Stephen too. So let me first introduce slightly the topic. So why are we here today? So with machine learning gaining lots of So welcome everybody to the second day of with machine learning gaining lots of popularity. We also saw, at least in the control community, that maybe the guarantees usually provided should maybe be changed a bit. It could be more sharper, could be towards the finite sample regime, etc. So the speakers of today, they made massive contributions in exactly this area. And not only on the control side, but also on the machine learning side. So really both ways, which I think is very nice. So on the one hand, perhaps the control community, they start to realize that they should provide more proper statistical guarantees. And on the other hand, the more machine learning oriented people saw the benefits of a principled system theoretic approach. And maybe I'm mistaken, maybe you could comment on this, but I think our speakers of today are also advocates of really combining the two instead of having two separate communities. So really taking the best of both worlds and using that to solve these problems. So our first speaker of today, Nikolai Matni, is an assistant professor at the Department of Electrical and Systems Engineering at UPenn. Before that, he worked with John Doyle towards his PhD at Caltech. He also did a postdoc there and at Berkeley, and I think especially at that time, he worked with Stephen too and others to provide these very inspiring works, which I think motivated many of us to go in this direction. So his research is also, like I mentioned before, it really uses all of these different facets of optimization, control, statistics to provide these very nice guarantees. So I think with all of this in mind, I think you'll be in for a fantastic talk today. And as far as possible, please join me in welcoming Nikolai Matni to the summer school. So the floor is yours.
All right, thank you, Wouter, for that very kind introduction. And thank you to you and all the other organizers for putting together this summer school, inviting Stephen and I to participate. So, good morning from Philadelphia, good afternoon if you're in Europe, good evening if you're tuning in from somewhere where it's later in the day. As Wouter said, I'm Nick Matni. I'm an assistant prof in the Department of Electrical and Systems Engineering at Penn. And the plan for today is I'm going to be kind of your tour guide this morning as we take a kind of a whirlwind tour of some of the relevant results from statistical learning theory and see how we can connect these up to ideas about dynamical systems and stability theory. And then we'll switch over this afternoon, and Stephen is going to show how you can use the tools that we developed this morning to derive some of the results that we've made in this space. So the plan for my first 4 hours here, which is going to be both long and I think go by really quickly because we've got a lot of material to go through, is first I'm just going to go over a couple of slides to motivate high level the results that we'll be talking today and why Stephen and I started working in this space of looking at nonlinear control and nonlinear stability and how that relates to sample complexity and generalization. And then I'll switch over to more of a lecture style session for the rest of the 4 hours. And like I said, we'll build up these theoretical and algorithmic tools that we need to understand some of the results that we've developed. Before I get the PowerPoint up, please don't be shy. If you have a question, either unmute yourself and just ask, interrupt me, don't worry about it. Or if you prefer to use the chat, I have the chat window open, so I'll be monitoring that as I go, and I'll do my best to answer all your questions. But yeah, basically going to try to make this feel a little bit more like a lecture classroom style thing. So that only works if you also treat it like a lecture classroom style. So don't be shy and interrupt me. Okay, so with that in mind, let me get up just a few slides here to kind of just motivate what we're thinking about at a higher level. And then, yeah, we'll dive into the details of things. Let's see, where's PowerPoint? There we go. Okay, everybody can see this and hear me okay?
Yep.
Awesome. Okay, so what I want to start with maybe is something that should be familiar to okay, so there's a question about the slides. Yeah, so I'm happy to share these slides, and I'm also going to share the lecture notes that we're going to generate with you. So if you want to copy stuff down as I'm going, knock yourself out, but you also don't have to scramble to do that because all of this will be shared. Okay, so what I want to start with is something that should be familiar to kind of everybody in the room right now, if you're coming from a controls background at least, which is just an overview of the classic system identification and control pipeline. If we're kind of doing sysid and then robust control, what does this look like? Oops. So let's assume that I start and I'm given my system. In this case, let's say it's a bipedal robot. And the first thing that I would do typically is write down a model. And we do this using some notion of first principles. In this case, I have the rigid body equations of motion, for example. Next up is, even though I have this first principles model, I might not know what all the different parameters are that define it. So I do some sort of parameter estimation step where I roll out the system, collect some data, and then solve a regression problem to get estimates of these matrices M hat, C hat, and G hat that represent the estimates of the inertial Coriolis and gravitational terms, for example. Next up, especially if we're concerned with robustness or safety, we may want to quantify the uncertainty associated with these estimates. And once we have a grasp on that, then we can use this quantification of uncertainty to solve either a robust or optimal control problem to close the control loop that guarantees not only some desirable performance, but also some notion of robust stability and safety. So this is kind of what I think of as like the Platonic ideal of what we'd like to be able to do when we're doing robust control. We're not always able to do all of these steps. Sometimes we skip some of them, but at a high level, conceptually, this is kind of the pipeline that's really been used for decades now. But one last thing that I want to say on the slide before we move on is I want to make something explicit about the overall paradigm here, which is that the notion of uncertainty that's emphasized in this classic control pipeline is that of model parameter error. There's some notion of a true underlying matrix M, C, and G, and we're bounding in kind of absolute terms the gap between these identified estimates and the true parameters. Okay, so keep that in mind as we move on to revisiting this from a more contemporary perspective. So what does this pipeline look like today if we're going to kind of try to bring in machine learning type approaches? So again, first of all, I'll start off with the same system. And the first big difference is in the modeling step, where now, for example, I could have some or even all of my dynamics be modeled by a rich function class, something like a deep neural network, for example. So modulo that, everything kind of stays the same for the first couple of steps in the sense that then I could proceed as before, collect some data and fit my model through some regression step where I'm going to try to find the, say, best neural network that captures the dynamics of this system. Okay, so the next big difference then is in the uncertainty quantification step. In particular, there is there's no longer any notion of a true model parameter with which we can bound errors. I know that my robot is not actually a neural network, not yet anyways. We haven't built any that are purely neural network in dynamics. So what we have to resort to instead is bounding some notion of prediction error over the trajectories that we've seen. And this in turn can be, for example, provided in some probabilistic manner. So that's what I have written here. I have some probabilistic bound that my prediction error is not too big. And then, once again, I can kind of use this uncertainty bound in the prediction error to formulate a possibly robust policy optimization problem, where now maybe even the policy and even the uncertainty representation may also be parameterized as a deep neural network. And the hope here is we want to be able to generate a safe controller. So this is kind of the way things are. This is not a bad description of the way things are done in a lot of kind of machine learning plus control space, in the machine learning plus control space. So what I want to highlight here, though, is that in this new paradigm, is we've really shifted to putting an emphasis on prediction error rather than model parameter error. This is out of necessity, right? There is no true underlying deep neural network. I don't have a choice. The only thing I can really reasonably talk about in this setting is the goodness of fit with respect to prediction error. But this brings with it an additional subtlety. And that's that these prediction errors only hold under the trajectory generating distribution that I used during training, right? So in particular, once I close the control loop, the trajectories that my system are going to see are going to follow a different distribution than the distribution that was used to of trajectories that was used to fit the model. And so basically what this means is that all of these guarantees that we may have worked really hard to get, they essentially go out the window. because we've changed the distribution. So we don't have any guarantees on this in the uncertainty quantification step anymore, at least not obviously. We have to do a little bit more work there. So from my perspective, this really points to a need to rethink the control pipeline to account for this distribution dependent uncertainty. So a couple of points that I want to emphasize. And the first is that, what I'm saying here is really not new or earth-shattering in any way. This is something, this distributional dependence and this issue of distribution shift from, say, training to test time has really been deeply appreciated and understood by both the reinforcement learning and imitation learning communities for a long time. But I want to kind of emphasize this for a couple of reasons. One is I don't actually think that this point is as well appreciated or as it should be within the controls community. And I also think that there's a real opportunity for the tools and insights of robust control in particular to be brought to bear on problems in safe learning and control if we can actually adapt this pipeline to be able to handle these distribution dependent prediction errors. So kind of just to motivate some problems where this could actually come up and be useful, I just want to highlight a few different settings where this kind of interplay between distribution dependent robust control theory and safe learning could potentially be beneficial. So the first one is this notion of safe model-based reinforcement learning. And here, the reason that we may have to deal with these issues of distribution shift is because as we update policies across epochs, and these policies are based on learned models and prediction error bounds, as we update the policy, the distribution might shift. Another thing that we may have to, area where this is kind of where this is an issue is in safe exploration learning. In some sense, this can be viewed as a subroutine for safe model-based reinforcement learning. And here the distribution shifts could occur, for example, due to having to expand the region of attraction of a system. And this leads to the system needing to actually be able to certify new out of distribution trajectories as being safe. Another context in which these ideas come into play is in the space of safe perception-based control. This was actually my original motivation for thinking about all of these problems to begin with. And here the distribution shift may come up. For example, if I start by using a state feedback-based controller to collect data for training. So assume that I have something like Vicon, I have motion capture, so I can actually get my states. And I do state feedback-based control. Then I fit a perception map or an estimate from, say, image as to where my system lives. And now I use an output feedback-based controller that takes the output of that perception map as inputs. So that could also lead to a shift because I'll have some new errors in my sensing and I'll go from state feedback to output feedback. And so that could lead to seeing different trajectories at test time than during training. And then finally, there's the idea of safe imitation learning, which Stephen will talk about in a lot more detail in today's second half of the talk. And here the distribution shifts would arise, for example, due to errors introduced due to mismatches between my learned policy and the expert policy. So if you ever heard that something like vanilla behavior cloning is really not very stable and kind of suffers from these catastrophic failures, this is essentially why I have errors in my learned map, in my learned policy, which means I deviate a little bit from what I saw during training. Now that I've deviated a little bit from that, the errors get bigger, and this keeps going on until my system blows up. Okay, so that's basically it for the high level motivation. But what I want you to take away from these first few slides is just that today's set of tools and the results that you'll hear in the afternoon, they're really being tackled in this broader context of trying to rethink the control pipeline to be compatible with distribution dependent uncertainty and how we can actually understand how the underlying stability and safety properties of the system translate into the corresponding generalization and sample complexity. Okay, so I'll stop here just really quickly and see if there are any questions. And then I'm going to switch over to the iPad and we'll kind of dive into the technical meat of the talk. Okay, well, it seems like we're all on the same page so far, so that's a good sign. We'll try to keep it going that way. So let me switch over to my iPad now. Just give me a quick second. iPad via AirPlay. All right, you can all see my notepad.
Yeah,
great.
that's good.
Okay, so today we're going to build up the tools that we need to analyze approximate solutions to the following two motivating problems. We're going to use these two problems to motivate all of the theory that we're going to look at in the morning, and then Stephen will kind of take over and look at what I'd call more research level type problems. So today we'll focus on understanding these two problems. The first one will be what I'm going to call prediction error guarantees. But we're not going to worry about distribution shift. We're just going to look to fit a model to fit a model that maps on that captures an autonomous system. So the setup will be that I have an autonomous nonlinear system, and I'm going to have that my initial condition, which I'm going to label with C for the whole day today. Whenever you see a C, that means an initial condition. That these are drawn from some distribution. So that's the only element of randomness that we're going to consider in this. There's no driving noise. There's none of that stuff. Just keep it really simple. The only element of randomness, the stochasticity, is where the initial condition is the initial condition from which I start my trajectory. And the problem that we're going to look at is we're going to try to solve and analyze the following risk minimization problem, which is to find some function that minimizes the expected value, where I have, let's call it C, drawn from that distribution of some loss that captures prediction error. So I'm going to use this notation here, x of t of c, to denote the state of the system at time t when I've started it off from the initial condition c, because we're going to need to kind of keep track of that. And here, here L, the loss function, is just some suitable map that takes state and spits out a cost, right, for some suitable cost function. So think of like a least squares cost or something like that. But we'll make this more precise later. So that's the first problem that we're going to look at. Then, depending on how we're doing on time, I'm hoping that we'll also be able to get to a policy optimization problem. And here, instead, I'm given a controlled nonlinear system. Again, the only element of randomness that we'll consider is initial conditions being drawn from some distribution. The screen has a black bar at the top. Do others see that as well? Let me see if I can fix that. Give me a sec.
So it's not very big. It's only crossing through the last words of your first sentence. So it's
oh, okay. So basically if I do that, it's okay, or
yeah.
Okay. All right. So I'll make sure not to write too high on the screen.
Yep.
Okay. So great. Yeah. Sorry about that. So we have our policy optimization problem. I'm given a controlled system. Again, my only randomness comes from initial conditions, and we're going to look to solve and analyze the following policy optimization problem. So I'm going to minimize over some policy pi, and we'll keep this simple in this context, in the sense that we're just going to look for a minimum norm, a minimum variance or minimum norm type cost. So here, just before, as I was saying, x of t of c is the state of my system being rolled out from the initial condition. Here, xt pi of c is state at time t, evolving under ut is equal to pi xt and starting from x0 equal to 2. Right. So we're gonna have to be careful in terms of all of this bookkeeping, because this is really all about how we're going to keep track of the corresponding distribution. So the goal is going to be to, what we're going to do is we're going to study these problems through the lens of empirical risk minimization. Or ERM. And what we're really going to care about is kind of understanding the map from, let's call it stability properties of my system. We're going to want to understand that, how that gets mapped to sample complexity. So that at a high level is what we're going to be after. We're going to try to understand how the underlying stability properties of, say, my dynamical system here affect the corresponding generalization bounds that I end up with. Okay. So that's our setup. So just keep these two problems in mind as motivation as we now start chugging through some perhaps more abstract theoretical results from statistical learning theory. But it's all, we're building up the tools to analyze these problems. So it's not just theory for theory's sake. Okay, so let's start what we're going to start with is an introduction to statistical learning theory. And in particular, a focus on ideas relating to generalization. Okay, so first of all, let's just give an informal definition of generalization. This is really something that it's a quantitative way of relating the performance of a model on seen examples to performance on unseen examples. Right, so nothing super complicated here. This is hopefully familiar with matches up with your intuition of what you thought of generalization was being. And we're going to study this now through the lens of risk minimization. So actually, let me go to the next page so that when I give you the notes, it doesn't get all messed up. So risk minimization can be set up in the following way. So here's our setup. First, I'm given some pairs x, y that live in some space x and y. And we're going to assume that x and y are jointly distributed according to some distribution B. All right, so you can think of x as, say, some input and y some output that I want to predict given x, for example. We also need a model, which is going to just be a map f that takes x to y. And we need a loss. And we'll call that L. That maps two outputs in the space of outputs to some real number that just captures the goodness of fit of, say, f of x relative to y. So the definition for the first definition is that of the risk of a model f with respect to a loss L. And that's simply given by the following expression. The risk of f, we're going to define it to be the expected value, x and y sorry about that. X and y distributed according to D. That way. X and y distributed according to D of my loss function as applied to f of x and y. And you can pose a whole bunch of different examples of things that we care about, things like binary classification, hypothesis testing, regression, even filtering as a risk minimization problem if you set up the space properly. So this is a problem that we want to solve. So let's actually just take a look, what we would like to solve. Oops. is the following risk minimization problem, which is going to be to find the best f with respect to this risk, right? So the best f of x, y, L, f of x given y. So there's some stuff that we can do to manipulate this to make it look a little bit easier, maybe. So let's see how far we can get in terms of just tackling this problem as is. So I can use the properties of conditional expectation to rewrite this in the following way. I can have an outer expectation over x, an inner expectation of y conditional on x, of the loss as applied to these two outputs given x, and then we're going to kind of wrap these expectations, right? So I've just used properties of conditional expectation, and for simplicity, we'll assume that there's a density. Assume that there's some density p of xy equal to p of y given x, p of x. This just makes things a little bit easier to work with, but all of this goes through without assuming the density. You just have to be a little bit more careful. But I can now rewrite this as this. That's better. Right, I can rewrite this now as, I'm just going to take the outer expectation and write it as an integral. So I can rewrite this as an integral over x of the conditional expectation of my loss and then we'll just integrate this over x. But what this form here makes clear is that I can just solve for a pointwise optimum. So because the optimization is separable, this implies that I could solve for f star as the argmin over, say, z of the expected value of y given x in this way. Right. Okay, so that's not bad in the sense that we made some progress here. We went from this really kind of nasty looking double integral to just this inner minimization. But what do we need to actually be able to solve this problem? So to solve this, I need to know the following. Right, so first off, I need to know, actually, let me do it this way, sorry. Right, I need to know the conditional density p of y given x of p of y given x, right? I need to know that to be able to evaluate the inner expectation here. So the question is f of x the immediate next step of a dynamical system, or does it represent the entire future trajectory? So right now, we're not actually talking in this setup here. F of x could be either. We're not limiting this to dynamical systems or anything like that. We're just thinking of a generic risk minimization problem. What we'll do later is set things up in such a way that f of x is the immediate next step of a dynamical system. Although there's nothing stopping us from thinking about multi-step prediction as well. And I can comment on that when we get there as well. Okay, so let me know if that didn't answer your question. If not, I'm going to keep going. So we also need to be able to,
yeah, sorry. Yeah, but thank you.
All right, sure. Great. Okay, the other thing that we need to do is we need to be able to solve, even if I do know this density by some miracle, I need to be able to solve this integral of L of zy, p of y given x, y given x, dy. Right. Typically, not going to be able to solve this in closed form. So this is, even if I knew the density, this is kind of a roadblock to begin with. And then even if I'm able to do that, I still need to optimize overall functions f, which is this nasty infinite dimensional problem. You know, typically none of these are known. We know I don't know the conditional density. I'm not able to solve the integral. And optimizing over all functions is a hard problem. So this is what motivates the idea of empirical risk minimization. And so let's talk about that now. So in particular, we're going to think about both the training set and empirical risk minimization. So the way that we're going to choose to approximate this nasty problem is as follows. We're going to be given a training set. We'll call that S, and it's just going to be a bunch of IID pairs drawn from our distribution. And we'll assume that we have X and we have N of them. Right? And I'm going to use this power here to indicate an IID draw. Right? So it's kind of the product space of these measures. So I'm given N IID samples. We can then define the empirical risk of a function f with respect to a loss L as, we're just going to take this nasty looking integral and we're going to replace it with the empirical mean. Right. So one thing that I want to highlight here, because this is going to end up being kind of the main focus of our study, is that this depends on training data S, which means that our S of F is a random variable itself. I'm going to use RV to denote random variable, depending on S. In potentially a very complicated way. So we're going to have to be able to deal with this, the randomness and the empirical risk. Okay. So we can then define empirical risk minimization as just solving for the best F with respect to this empirical loss. So I could define, let's call it F star sub S to be equal to the argmin of F in some function class F, which I'll describe in a second, of my empirical risk. So a few comments are in order right now. The first is F is usually a function class that is easy to optimize over. Right, so this could be, let's say, the set of linear predictors with some bounded norm. This could be a set of deep neural networks. It could be a set of kernels, something living in an RKHS. You know what that is. But it's going to be something that we can efficiently optimize over. And then the other challenge is, just as the empirical risk was a random variable, F star of S is also a random variable, depending often in a very complicated way on the training data S. That's going to be a source of headaches for us later on. We're going to have to be able to deal with that well. Another thing that's worth noting is that F star of S may not always be exactly found. And it may not be unique. Right, so why am I saying that F star of S may not be exactly found? Essentially, unless I can solve this problem here in closed form, I'm going to have to resort to some sort of iterative algorithm, something like gradient descent or SGD or ATOM or your favorite variant thereof, to get an approximation of it. And we're going to want to make sure that our theory extends to this case too. We don't want to have to depend on having the exact argmin. So to avoid confusion, though, I'm going to label, we will use F hat of S to denote the output of ERM, right? Just to kind of indicate that sometimes this F hat of S is not necessarily going to be the exact argmin. And then finally, just to introduce some terminology, RS of F hat of S is called the training error, loss, or risk. So these are all used interchangeably. Okay. So why would this work? Why should this work? Well, ideally, what could we hope to come out of this? So the ideal scenario is that my RS of F hat of S, my empirical risk, my training loss, is approximately equal to the true risk. Right. Ideally, this is the case, and that's in that case, I'll know that my empirical risk looks like, that should be, yeah, looks similar to the true risk. So it's a good representation of reality. So there's a question here which is saying, how do I know that F star of S exists in the first place? If it didn't exist, then we will always end up with hat F of S. Yes. Right, that's absolutely true. So I could replace the argmin with an arginf if you want, and that kind of will get you in the same place under some suitable assumptions of regularity, obviously on the loss function. So in our setting, and we'll get to this later, we're always going to assume that the loss function is bounded, so it lives within a certain set of values. So if you combine that with enough additional regularity assumptions, then F star of S should exist. But your point is absolutely correct in the sense that even if we're in a scenario where F star of S didn't exist, wasn't achieved within the function class or anything like that, we always end up with F hat of S and nothing's going to break. We're going to do everything assuming that we only have our hands on F hat of S. And then we kind of go the other way where nice things happen, and by some miracle you're actually able to get F star S, and you can just replace F hat of S with F star of S. That's a great question. Okay, so this is what we would like to happen, right? We want our empirical risk to look close to the true risk. But what ends up happening usually is we have that our empirical risk is less than our true risk. And this kind of makes sense in the sense that this is some function that I've picked up specifically optimized over the samples that I've seen, and one would expect in general for this not to generalize exactly as well to the true population risk or the true risk over the actual expectation. So with that in mind, what we'll do is we'll define the generalization gap or error. We'll call this delta gen of F hat of S, and that's equal to R F hat of S minus RS F hat of S. So the true risk minus the empirical risk. And we want to make this kind of as small as possible. Right, and then the other thing is, I'm defining this right now in terms of F hat of S, but this also makes sense for any function that I plug in there. If I just take some F and look how it does on the empirical risk, I can talk about the generalization gap associated with that as well. So here's here's the big theory of all of machine learning. This is really the fundamental theorem. Which is that I can take my true risk with respect to some function and rewrite it as the empirical risk plus the generalization gap. So I was kidding. This isn't a deep theory, but this actually ends up being the starting point for everything that we're going to be thinking about. So again, the way to think about this is I see this during training, and this I want to keep this small. Right. So the idea is I see this during training and I want to push it down as much as possible, but I want to make sure that my generalization gap doesn't blow up on me. Right. So what I'd like to do now is just take a small detour to talk about how a bias variance trade-off interpretation of this can be taken, and also to comment on the modern regime of over-parameterization. This is going to just be a small detour, but I think it's an important one. Okay, so again, we're going to define our empirical risk to be the min over f and f of, oops, there shouldn't be a hat there. Right, so let's put an approximation there just in case it doesn't exist. So here's the mental model that you should kind of have. Right, one is that you can think of the empirical risk R S of f hat S. You can roughly think of this as my model class F's bias, right? In the sense that if I don't pick an F that's sufficiently expressive, then it may be hard for me to push down this empirical risk. So as an example, if I have a linear classifier, for example, and I just allow the weight, the vector defining the linear classifier to be of arbitrary norm, I can almost always push down my empirical risk very, very close to zero if things are linearly separable, for example. And then we have another term which I'm going to introduce informally to start, and then we'll formalize this, is the complexity of my model class F. So how expressive it is. And you can think of this as my model's variance, model class F's variance, or ability to overfit. So this is kind of the mental model to have in mind. And this is the standard picture of what this ends up usually looking like. So I'll have my x-axis here be the complexity or capacity of F. And I'll have this be my empirical risk. I'll have this, or just the actual risk that's achieved. Right. So the first thing we can do is look at the training risk, which will say, start up pretty high, and then as my complexity gets bigger and bigger, I'm eventually able to fit all of the data. As soon as I have the same number of parameters in my model class as I do, say, the number of data points that I have, if there are no additional restrictions, for example, then I can always fit things exactly. But this is my training risk. The true risk will look somewhat different. It'll look something more like this. Right? It'll go down. No, I don't want that to be straight. It'll go down with my training risk, and then it'll eventually start coming up. Right? So this is my true risk. And the way to think about this is I can kind of divide things here. Right? That's kind of the sweet spot. Right, so in principle, when you're say cross-validating and trying to pick your regularization parameter, this is what you're hunting after. And in this regime, I'm underfitting, and in this regime, I'm overfitting. Okay, so this is the classic picture. This is the bias variance picture. It's in pretty much every classical statistical textbook or machine learning textbook. So what's happening now? What happens in the world of deep neural networks, which completely break this paradigm? What you see now is that there's this point here, which is called the interpolation threshold. Which is roughly, you can think of this as the capacity, or I'm using complexity of F is equal to the number of data points that I have. Where this is the minimum complexity at which I'm able to interpolate my data. But what we see now is if you go beyond that, you end up with seeing your true risk getting smaller and smaller as my complexity grows up. So this is kind of this idea of double descent, if you've heard about that. kind of made a big splash in the deep learning community a few years ago. So there's a couple things that I want to say about this. The structure of this kind of peak thing where I descend, go up, and then come back down, that's not universal. In the sense that, if you regularize in a specific way, you can end up with no double descent or even multiple humps, etc. What is fundamental, what is universal, is that if as my complexity goes up in the interpolation regime to the right of the interpolation threshold, the risk goes down. Right? The fact that this idea that if I become more and more over-parametrized, the better my generalization error, which is completely flies in the face of kind of the old bias variance trade-off, this actually happens. Whether there's a bump in the middle or not, that you can kind of play around with that based on regularization and get rid of it. Okay, so the key takeaway here, and the reason that I'm making this detour, is that in the modern regime, if you showing that, let's say my delta, the generalization error of f, if that scales something in a way that's proportional to the number of free parameters divided by number of data points, it's vacuous. In the sense that we're often going to be in a regime where I have actually more free parameters than I do have data points. So there's not going to be a way for us to show that the generalization gap goes this way. So we're going to do our best to avoid such bounds, to avoid bounds that depend on the number of free parameters, say, defining my function class f. What we'll see is that in some of the dynamics and control settings, currently we're actually kind of stuck with bounds that look like this. We don't think that this is fundamental, but rather we think it's a limitation of our proof techniques. But I'll be sure to highlight those when they come up and explain when they are or aren't a problem. But this is just kind of an important piece of background knowledge that I think anybody in this space should know. So there's a question that's asking on the relation between generalization error and degradation effect in the overparametrization regime. So I don't know what degradation effect is. Could you maybe expand on that a little bit? Feel free to unmute yourself.
Hi, Nikolai. So thanks for the lecture. So the degradation effect is what motivated, for instance, the introduction of the residual connection in ResNet architecture. And it's basically by stacking multiple layers in the overparametrization regime, you can observe that the generalization is not degrading. It keeps, as you have in your plot, it keeps improving, but at the same time, your training error is kind of starts degrading. So the network is not learning anymore, despite the addition of these extra layers, so more parameters.
I see. Okay, so let me preface this with the fact that this is the first that I'm kind of hearing about this broad idea of degradation effect. I'm not an expert in deep learning in any shape or form, but here's my interpretation of it based on what you just said, which is, it sounds like as the networks get deeper and deeper, what you're ending up with is an optimization challenge, in the sense that it's harder to train these networks down to, say, zero empirical risk, even though in theory they're capable of doing that. So what this plot here does not capture the notion of difficulty of optimization. There's kind of this assumption that I'm able to, say, train my model all the way to optimality on the training risk. So this is absolutely not capturing that idea, in the sense that we're kind of making this assumption that at some point I hit my training risk goes to 0. And as I make my model bigger and bigger, it's never an issue that the training risk comes back up. I think a more involved and in-depth study of the trade-offs involved with the sample complexity, say involved with training things, is an interesting and important one, but it's not something that we're going to touch on today.
Many thanks.
Yeah, of course, that's a great question. And thank you. I learned something today as well about this degradation effect. That sounds really interesting. Okay, so with that in mind, with this picture in mind, we're going to start developing a set of tools for thinking about this. So, sorry, Siri got triggered and she's telling me that she's mad at me right now. I don't know how to turn this off. Give me one quick sec. Okay, there we go. Can still see my screen okay?
Yes, perfectly.
Yeah, sorry about that. No, sometimes Siri hears me and thinks I'm asking her questions, but I'm not. Okay, so there are a lot of different theories of generalization. And what I mean by that are there are a lot of different theoretical tools that can be used to guarantee that my generalization gap doesn't get too large. Right? And I want to highlight some of these because they're important to know about, even though we're only going to discuss one of them in detail today. So one is algorithmic stability. And what this says is that if I have a model that's output by a learning algorithm, right? And a learning algorithm is just something that operates on my training data and spits out a function, right? So we could think of it as, call it f hat of s is equal to a for some algorithm operating on my training data. Models, so if I have algorithmic stability, this means that models output by a learning algorithm are insensitive to perturbations in the training data. Right, so more formally, what this kind of means is something along the lines of, I have that A of S minus A of S prime is small if the gap between my two data sets that I'm using is small. This then gives me, this gives us generalization that generalize well. Right, so this is kind of this idea that if I have a training set, and let's say I take one data point from the training set and swap it out adversarially with any other training point within the space, and I rerun my learning algorithm, the output of my learning algorithm shouldn't change too much. And if you could do that, then you can show that this leads to generalization. Another approach is the notion of uniform convergence. And this is what we're going to talk about today. And this says that generalization happens when, oops, that's not how you spell when, F is simple. Right, and measures of simplicity include things like VC dimension, Rademacher complexity, etc. Right, and this is what we're going to talk about today. There are a couple of other things that I want to just highlight. There are other methods that are based off of margin bounds. And these say that when the data is easily separable with some margin specifically, then I get good generalization. And then last but not least, there's this notion of optimization as well, which is essentially capturing the fact that algorithmic choices can yield models with good generalization properties. Right, so an example of this would be, for example, a very simple example would be, say, I want to solve a least squares problem, just a linear least squares problem, and I use gradient descent to solve it. And I initialize my gradient descent algorithm at 0. We know that that converges to the minimum norm solution if I have an underdetermined set of equations. So that's an example of how algorithmic choices can yield models with good generalization properties. Good generalization properties. We've also seen lots of studies looking at, say, for example, why stochastic gradient descent leads to good solutions, things like that. So that's an example of this. But as I mentioned, today what we're going to talk about is this notion of uniform convergence. So typically, there are two scaling regimes. For these kinds of bounds. So one is when my empirical risk is large. And large here just means not 0. We'll show that we should expect that delta gen of f, the generalization gap, will scale something like 1 over square root n, where n is the number of data points. There's another regime, though, which is perhaps a little bit less appreciated, but that's very important, especially in the context of dynamical systems where data points are, say, trajectories, which is that when Rs of f is actually close to or equal to 0, then we expect the generalization gap to instead scale like 1 over n. So that's what's called a fast rate. Okay, so I'm saying we expect this to happen. Why? Let's take a look at why we would expect this to happen. Okay, so to get intuition, what we'll start with is we'll study the behavior of a single f and f. So I have my function class, and I'm just going to pick one of these functions arbitrarily. And we'll do this on the 0, 1 loss f of, the loss as applied to f of x, y is equal to the indicator function of the sine of f of x is not equal to y. Right, so in this setting, my y's live in, let's say, plus minus 1, and my x's live in some other space. And I want to take a map from that space to f of x, and then check the sign of it. If the sign of it matches the label y plus or minus 1, then I don't incur an error. If I get a mismatch, then I incur a loss of 1. So let's make some observations about this. We can reason about our loss function as a random variable. And in particular, this thing is equal to 0 or 1. So it's a Bernoulli random variable. Oops. With some probability p, and I'll label it as pf to indicate that this probability will in fact depend on the function that I'm studying. For some pf living in 0, 1, and then that is also equal to the this pf here is also a way to interpret it is equal to the probability that my sign is not equal to y, right? And this is with respect to this joint distribution. Okay. So now we'll make a few observations here to kind of connect up this loss function to a true risk and an empirical risk and reason about whether they should be close to each other or not. So next, let's make the following observations. So first of all, I have that the true risk achieved by a function f is the expected value of d with respect to the distribution d of this indicator function. And this is equal exactly to PF, right? It's the probability that there's a mismatch. The expectation of an indicator is just the probability. Let's now define our empirical risk as 1 over n, these indicator functions. Right, so let's kind of notice, let's take a look here, right? So this empirical risk is an empirical average of these IID Bernoulli random variables. Right, so we already know that by, for example, the strong law of large numbers, I will have that my empirical risk will converge almost surely to my true risk. Right, so in other words, we're saying that my true risk will converge to, sorry, my empirical risk will converge to my true risk with probability 1. So this is, the classical picture. This would say that this is a consistent estimator or something like that. But what we want is a quantitative measure of how quickly this happens. Right. And to do that, we're going to need to bring in some tools from concentration inequalities or concentration bounds. And so I'm just going to introduce a standard tool, which is Hufting's inequality. And I'm going to do this for bounded random variables. So for those of you who know what a sub-Gaussian random variable is, all of this extends to the case where instead of having things be bounded, they're sub-Gaussian. But I want to keep the technical overhead as low as possible, so we're just going to stick with bounded random variables. So here's the statement of Hufting, which says that suppose that I have some random variables, x1 through xn, that are independent random variables and lying in AI, BI almost surely. Right, so this idea that each of my independent random variables, x1 through xn, they live in some interval almost surely. So they're all bounded. Now I'm going to define z sub n to just be the empirical average of these xi's. Then what Hufting says is the following. We have that the probability that z is greater than or equal to the expected value of z plus some parameter t is less than or equal to this exponential decay rate of 2n squared t squared over the sum of the ranges squared. So this gives me a quantitative measure of how quickly z converges to its mean, and essentially this tells me that the probability of this error happening or this larger deviation happening decays exponentially in the number of data points that I have. Okay, so we're not going to prove that. We're just going to use that as a tool that we can apply. So what we'll do now is we'll apply Hufting to with the following identifications. I'm going to set xi from above. Actually, I'm going to put tildes here just so we're not confused about notation. We're going to set these guys to be equal to this indicator function. that captures errors. Right? Trivially, this lives in 0, 1, right? It can only take on values of 0, 1. And then I'm going to set z sub n to be equal to the negative empirical risk. And the reason I'm putting negative signs here is just we want to flip the inequality. We care about the empirical risk bounding the true risk. And then expected value of Zn then becomes the negative risk, and I'm going to set t equal to epsilon. Right, so if you kind of just plug this through, we see that the probability of the over the samples of the risk of f minus the empirical risk of f being greater than or equal to epsilon is less than or equal to negative 2n epsilon squared. And the reason that the n drops off is that down here I'm basically summing together n times 1. So that's where the factor of n goes away. Okay. So now what we're going to do is now we invert the probability bound. By setting the right-hand side equal to delta. So when people say I want to invert the probability bound, that's what this means. So essentially you set delta equal to the right-hand side. Right, so this is saying I want to understand how much of a deviation I can tolerate such that my error will always be less than or equal to delta. And then you solve for epsilon, and this ends up being equal to square root of log 1 over delta over 2n. Right, which allows me to conclude that with probability, at least 1 minus delta, we have that our generalization gap for f, which is equal to r of f minus rs of f, is going to be less than or equal to epsilon, which here is going to be square root log 1 over delta over 2n, which, as we had hoped, is order-wise 1 over square root n. So this is the rough intuition of where the where the idea that if my empirical risk is non-zero, then I can apply some concentration bound, and I'll get a 1 over square root n type convergence. Now let's look at what happens if the risk is actually equal to 0. What if my empirical risk is equal to 0? So I'm able to say perfectly classify all of my training points. So can we do better here? So let's make the following observations. First of all, my empirical risk is equal to 0 if and only if I have that the indicator function applied to f of xi is equal to yi, right? That I'm able to get things right. I want to get this right for all xi, yi in my sample set. So what we're interested in bounding then is the following probability. So it's the probability over my data set that for all I get things right. But in reality, my true risk is big. It's bigger than epsilon. So the way to read this, and remember that this is equal to the probability of just some generic point of making an error on a test point. Okay. So here's the way to read this. What you have essentially is you're trying to understand the probability that S tricked me, my training data tricked me into thinking F is a good classifier. Right, that's what this expression here is capturing. Given that F is a bad classifier. where here bad means R of F is greater than epsilon. Right, so this is kind of the way to read this. Does that make sense? Yeah, okay, cool. So with that intuition in mind, what we're gonna just do now is rewrite the above probability by exploiting the fact that I have independent data, or IID. So I can rewrite this as a product, 1 to n of the probability over each of the xi, yi distributed according to d, that the sign of f of xi is equal to yi, given that the probability of some xy distributed according to d of the sign of f of x not equal to y, this probability of error is greater than epsilon. Right, so I'm basically just formalizing this idea of the probability that S tricked me, given that F is a bad classifier, and rewriting that first probability here as a product of probabilities by exploiting the independence of the data. So I don't have a bound on this, but I have a bound on the flip side event. So we can rewrite this as the product from I equal 1 to n of 1 minus the probability of xi, yi distributed according to my distribution not equal to yi, given the same thing as above. Okay, but what I'm essentially saying is that this thing here is greater than epsilon, right? That's the assumption that we're conditioning on. So this whole thing, this whole expression here, just kind of trivially, this has to be greater than epsilon, because I'm conditioning on the event that this exact probability is greater than epsilon. Right, so at this point, we're basically done. So I can rewrite this as the product 1 to n of 1 minus epsilon. Sorry, not equal, but rather less than or equal to. And this is equal to 1 minus epsilon to the n, and I can upper bound this by e to the negative epsilon to the n. Right, so essentially what this is saying is I need to see n 1 minus epsilon probability events to be tricked by this. So these, the larger n is, the smaller the probability of seeing all of these different points. And now again, if I invert, so what we can conclude from this rather is that the probability that my empirical risk is 0, given that the true risk is greater than epsilon, that's less than or equal to, which is exactly what we cared about, is less than or equal to negative epsilon, to e to the negative epsilon to the n. Inverting, we conclude that with probability at least 1 minus delta, I have that delta gen of f, which is equal to risk of f minus rs of f, but this is equal to 0, is less than or equal to log 1 over delta over n. And this is exactly equal to the scaling regime that we wanted. Okay, so this intuition that we just saw carries over through to analyzing the output of an empirical risk minimization problem, as opposed to just some arbitrarily picked function. But the challenge is in characterizing, in carrying over the analysis to f hat s is f hat s is emphatically not independent of the training data of s, right? So I can't apply things directly because there's going to be all these really nasty correlations between the f hat of s that I put in here and the actual data. I wouldn't, for example, be able to split this product up. Everything is now dependent because we're mixing everything up. So we're going to need to develop a new set of tools to handle this. And this is going to be the idea of uniform convergence. Okay, so I kind of view this as taking a bazooka to the problem in the sense that we're going to show that delta gen of f is small for all f in f. Right? And this is why it's called uniform convergence, because you're showing uniformly across the function class that my empirical risk converges to my true risk. And the reason I think of this as kind of taking a bazooka to the problem is the sense that we're guaranteeing that the empirical and true risk come close to each other for all possible functions, even functions that are really, really bad on the data and that we'd never actually have output by an empirical risk minimization. So inevitably, the bounds that we're going to get are going to be somewhat conservative. That being said, they're still instructive in terms of understanding the underlying hardness or easiness of a problem. So we'll start with a warm-up, which is we're going to assume that my function class is actually finite. Right, so this consists of just a finite number of functions that I can pick from. This is actually not a bad model, for example, if you're assuming that you're implementing things in floating point operation, This is, this will roughly scale like 2 to the 64 or something like that. And we'll see that that actually doesn't completely blow up our bounds. Okay, so let's define the event E sub f, and this will just be the event that I have that the generalization error of f is greater than or equal to epsilon. Right, so essentially what I'm trying to bound is the probability with randomness over my data set that there exists an f in my function class f such that delta gen of f is greater than epsilon, right? Such that this event E happens. Another way to say this is I can write this as a union over those events, right? The union over f and f of the event f. Right? And don't forget, f is a finite cardinality, so this union is well defined, and there's nothing to worry about there. And I can then apply the union bound to say that this is less than or equal to the sum of these guys. Right, and this is exactly equal to the probability, the sum over f. This is essentially equal to, because these are all going to be the same. Actually, let me do it this way. This is equal to the sum over f and f, that the probability over my data set is that my delta gen of f is greater than epsilon. Right, but we bounded exactly this in the single function setting, in the single function case. So this is less than or equal to the cardinality of my set times this exponential term. Right, this is exactly what we had bounded previously in a single function case. Again, if I now invert this, I can conclude that with probability at least 1 minus delta, I have that delta gen of f is less than or equal to the square root of the log of my cardinality over delta. This used to be a 1, now we have it with the cardinality of the set divided by 2n. And this holds for all f in f. In particular, this will also hold for whatever gets spit out by my empirical risk minimization problem. Okay, so this is always a good first sanity check in terms of what to do, what to check to make sure that your problem is well posed. But what this allows us to conclude, though, is what we'll see is that in general, our bounds will look like something that scales like square root complexity of f divided by n, by square root n. That's kind of the rough structure that we're going to see. And the question now is how are we going to capture this complexity of the model class f? So to generalize to F of infinite cardinality. There are many different measures. Measures of complexity that you may have heard of. Right, so we have things like VC dimension, the covering number of a set, and say Rademacher and Gaussian complexities. Now, these all are, with maybe the exception of VC dimension, these are all pretty much equivalent to each other up to certain bounds and constants. What we're going to work with today is we're going to focus on Rademacher complexity. And when I can, I'll make some connections back to VC dimension and covering number, for example. Okay, so let's define the Rademacher complexity. Of a function class F. This is going to look a little daunting at first, but we'll parse through it and kind of get our intuition about what it's doing. So our setup is, again, we're going to have our training set of these data pairs drawn according to my distribution. And going forward, we're not really going to need for at least a little bit to distinguish between xi and yi, so I'm just going to call them jointly zi. Just to kind of to shorten notation. And then we're also going to let the following collection of sigma I equal 1 to n, be a collection of Rademacher, IID Rademacher random variables. That just means that sigma I is equal to +1 with probability 1/2 and -1 with probability 1/2. Right. So the first thing we're going to do is we're going to define the empirical Rademacher complexity in the following way. I'm going to call it R hat n of some function or some hypothesis class or function class H to be equal to the expected value over these Rademacher variables of the supremum over my function class of the following strange looking expression. So it's kind of it's a mean on my training data, and I'm multiplying each of the training points by this Rademacher random variable. Can everybody see that okay? I know I'm a little bit close to the edge there. Is that readable, or should I rewrite it?
I think it's still readable.
Okay. If you're not sure what, it's also something I forgot to mention. I have really bad handwriting. It's just, I know that I do, and as I get tired, the handwriting gets worse and worse. So if at any point my scribbles become illegible, just interrupt me, and I'll recognizantly be careful about my writing. Okay, so once I have my empirical Rademacher complexity, I can define the true Rademacher complexity, or just the Rademacher complexity. And we're going to denote that by this script R sub n of h. And this is just equal to the expected value over my training data of the empirical Rademacher complexity. Okay, let's try to get some intuition as to what the heck this is doing, because this is kind of a nasty looking expression. So the first thing to think about is to look at the inner expression here, just this sum, and forget about the randomness, just fix the sigma I and fix the zi. What this is measuring then is the function class's ability to correlate the data to a random binary signal, right? The sigma i's are all plus or minus 1 at random. And so what this, oh, sorry, this should not be an F, this should be an H. And so what this inner expression here, or if I just fix a sigma I and a zi, a set of data and a signal sigma I, I'm measuring the ability of my hypothesis class or my function class H to correlate a data set to a binary signal. Now, if I take an expectation over the sigma I, then essentially what I'm doing is I'm measuring H's ability to fit a fixed data set to a random signal now, on average. And then if I take the expectation with respect to the data set, I'm now looking at the essentially H's ability to fit a random data set to a random binary. And so this, at least intuitively, should inform why this is a reasonable measure of complexity for a function class, because the more expressive my function is, the easier it'll be for me to fit a random binary signal. Whereas if I have a very unexpressive function class in the extreme, if I say H is just 0, then I'm never going to be able to fit a binary random signal. I'll always get 0 out of this. So that's kind of the way to think about this. So here's kind of the main generalization guarantee that's connected to Rademacher complexity. If I fix a failure probability, delta in 0, 1, and I assume that my hypothesis class, my function class, is a subset of the set of functions that map my inputs, my data to some bounded interval, and we'll just make sure, we'll just assume that it's between 0 and b. And I can always make sure, I can always have it lower bounded by 0. If H is bounded below, I can just shift it, and we're going to assume that it's upper bounded by b. And then this is, of course, for our training data equal to Z1 through Zn, and that's distributed IID. Then we can say that with probability, at least 1 minus delta over my training data. And for all functions H in the model class H, we can prove that the expected value of H of Z is less than or equal to its empirical mean plus twice the Rademacher complexity of H plus B, which is the bound on my loss function, times the square root of log 1 over delta over 2n. Right, so we very nicely capture this idea of the empirical risk being some notion of bias and this Rademacher complexity being some notion of variance, in the sense that we'll see that as I make H more expressive, I can push this down more, but correspondingly, the Rademacher complexity will increase. So you want to balance the two. We're actually going to prove this theorem because I think it introduces some pretty cool techniques that are worth knowing. So here's the proof. Actually, I'll skip to the next page so it's not cut off. So we'll first start off with some very simple observations, and then things will get a little bit more tricky as we proceed. So the first thing that we can do is write this right-hand side, this left-hand side that we care about, as this empirical mean plus the difference between the two. Right, this is just the standard idea of adding and subtracting my empirical risk. Now, the first thing I can do is I can certainly bound this by the supremum of this expression over the function class. Right, just by the definition of the supremum. Okay, so now what we're going to deal with is bounding this expression. Because if I can bound this expression and get it to look like this, get it to look like this expression here, then I'm done. So the first thing we're going to do is I'm going to define a random variable that depends on my training data as exactly this right-hand expression. So this is going to be the supremum of the true expectation minus the empirical expectation. The first thing we're going to do is we're going to show that phi of s concentrates around its expected value. To do this, we're going to need to introduce another type of concentration inequality, which is another very powerful one. And between Hufting and this lemma that I'm going to introduce here, which is called Mcdermott's inequality, you can get very, very far. So the lemma here, which is known as Mcdermott's inequality, says the following. Let Z1 through Zn be independent RVs, taking values in some set Z, and suppose that I have a map phi that takes the Cartesian product of Z, so Z1, Z2, Z3, etc., and maps it to some real number, and that it satisfies the following bounded difference condition, which is saying that if I take a supremum over Z1 through Zn and some Zi hat term of the difference between phi evaluated on Z1 through Zn and phi evaluated on the same set data set, except I'm going to switch out the ith position with this hat term. If this satisfies that it's less than or equal to Ci, and I'm going to label this as star because I'm going to need it later, then, and this needs to hold for all I, then we have that the probability here, and this is going to be again over my data set, that phi is greater than or equal to its expected value plus t is less than or equal to an expression that looks very similar to what we saw previously, negative 2t squared over sum I equal 1 to n of Ci squared. So this basically says if I have a well-behaved function or map phi, that where well-behaved means that if I take any slot, any point in there and just adversarially switch it out with another point, the largest deviation I can get is the Ci. If this holds for each entry of the inputs to phi, then I get this Hufting-like concentration inequality. And so this is actually more general than Hufting. So here, as an exercise, if you're interested, you can derive Hufting from Mcdermott. Right, so as an exercise, if you want to do it later, you can derive the Hufting inequality that I showed you previously from Mcdermott's inequality in a quite straightforward way. Okay, so let's go back to our main proof now. To main proof. So I'm not going to do this, but it's not too hard to check that the random variable phi of s that we defined above satisfies this bounded difference inequality. And not only that, it satisfies it with the same Ci for every I, and that's just equal to B over N. Right, intuitively, it just kind of makes sense if you look at it. You know, I'm looking at the difference. If you get rid of if we got rid of the supremum here, for example, and just fixed an H, it's obvious that that's the case. Because I subtract the two off from each other, these expectations cancel, and then I'm just looking at the difference of empirical risks. And the only thing that's left is the slot where I differentiate a thing, where I swap the thing out, so I end up with B over N. So it's not too hard to check that. What we're going to do then is apply Mcdermott's to conclude that with probability at least 1 minus delta, I have the following, that the following holds. We can rewrite our expectation So in the interest of time, I'm going to just kind of I'm going to invert the probability bound and integrate it into the inequality that we have at the top. So what we've done essentially is we've replaced the supremum with its expectation of the supremum of H, and H of expected value and then we have a statistical rate term that will come from inverting the probability bound, which will look like log 1 over delta over 2n, and the B pops out output. Okay, so this is now what we have to deal with. And this is already starting to look Rademacher complexity-ish. We have the supremum inside of an expectation. And this is where now we're going to use a very powerful trick from probability and analysis, which is this notion of symmetrization. So the trick is to introduce what's called a ghost sample. S bar. So these are just going to be another n IID copies of our training data. And what's nice about this is that we then have the following properties. I can rewrite the expectation with respect to D of H of Z. I can rewrite this as an expectation of over my ghost sample of 1 over n sum over I equal 1 to n H of Zi bar. Right, just linearity of expectation, and all the Zi's are IID. So this is nothing particularly deep at this point. And then we have another nice property, which is that 1 over n over our original sample, I can put an expectation with respect to the ghost sample around it. And it's not going to change anything. And that's because S and S bar are IID are independent. Right, so I'm taking an expectation of some random variables with respect to other random variables that are independent of it. So it doesn't change anything. All right, so why do we want to do that? Because then this allows me to write the expectation of the supremum here. I can replace this inner expectation over a single data point to an expectation over my ghost sample. And I can now write this as 1 over n H of Zi bar minus H of Zi. Right, and so this is why it's kind of called symmetrization, because we're making this expression on the inside here look a lot more symmetric. And now we're going to just pull the expectation out of the supremum. We can always do that with an inequality. All right, so this is getting close to what we want it to look like. And now what we're going to do is we're going to exploit some nice properties of Rademacher random variables. So my first claim is that I can add, I'll rewrite it. I can actually write with equality the following statement. So I have an expectation over my two data sets. And now I'm going to add an expectation over Rademacher random variables. And that I'm going to claim that these are the same. Okay, so why are these the same? The sigma i's are equal to plus or minus 1 with probability 1/2. So essentially, that this is just, all this is saying is that with probability 1/2, I'm just switching zi and zi bar from s to s bar. I'm just relabeling things. But in expectation, nothing is going to change because the initial data points are all of the data points across s and s bar are all IID. So I'm just relabeling IID random variables. This isn't going to change anything. And now we can just split this up and use linearity of expectation. So this expectation, I'm not going to write the argument anymore, but it's with respect to the two data sets as well as the Rademacher random variables. This is certainly less than or equal to the supremum over h of 1 over n, I equal 1 to n of sigma I h of zi bar, plus the expectation, actually, I'll do it. I think it's important. Plus the expectation over s, sigma I, supremum of h, 1 over n, I equal 1 to n, negative sigma I, h of zi. Right, I gave my supremum more power. I allowed it to pick each of the functions that appear in each term individually. Of course, the other thing to notice is that this is equal in distribution to my original sigma I, right? If I have something that's equal to plus or minus 1 with probability 1/2, and I put a negative sign on it, it's still equal to plus or minus 1 with probability 1/2. So I can rewrite this as supremum over h in h plus the same thing over s. Right. I just don't want to I'm just saving myself a little bit of writing. But what is this? This is exactly the Rademacher complexity of h. And this is the same thing, just over a different data set. So this is exactly equal to 2 times the Rademacher complexity of h. Okay, so what I'm going to do is we're going to work through a last example of applying this to binary classification with the hinge loss, and then maybe we'll take a short break. And then the second half, we'll look at how to apply these ideas to dynamical systems. So here's some useful properties of the Rademacher complexity. So one is, let H be a function class and define AH plus B to be equal to the set of G of X equal to AH of X plus B. We then have that the Rademacher complexity of AH plus B is just equal to the absolute value of A times the original function class Rademacher complexity. This is really easy to prove from the definition, so I'm going to leave that as an exercise. Here's another important one. Let F be a function class. And suppose there's a map H taking R to R that is, oops. We're going to assume that this is LH Lipschitz. And that H of 0 is equal to 0. Then we have that the Rademacher complexity of H composed with this function class, which is basically H of F of X minus Y, for example. This is less than or equal to twice the Lipschitz constant times the Rademacher complexity of the underlying function class. This is not obvious. This is known as the Ledoux-Talleyrand inequality. Okay, so these are the two properties that we're going to need to rely on for our next example. So our example will be binary classification with a hinge loss. So I'm going to define the function LF of Z as shorthand for L of f of x, y. And this is going to be the hinge loss applied to it. We're going to do 1 minus y times f of x, and we're going to take the max with 0. So this plus is just I'm projecting it onto the positive real line. I'm going to define a bound on my loss function in the following way. I'm going to call this the supremum over x in x, y in y, and f in f of L of f of x, y. So I'm going to leave this just as this abstract definition, and then we'll actually compute this when we fix the function class. And then we're also going to allow L composed with f to be specifically these functions L of f that I defined up above, such that f is in some underlying function class cal f. So with this setup, I can just immediately apply that with probability at least 1 minus delta, that my true risk, which is LF of Z, is less than or equal to my empirical risk, which is the LF of ZI, plus 2 times the Rademacher complexity of L composed with F, plus this bound times the statistical rate term. This is just an application of the theorem that we just derived up above. So what we need to work with now is we need to figure out how to bound this Rademacher complexity term. So let's make some observations. So first of all, notice that I can write L composed with F as L tilde composed with F with this plus operator acting on it, where I'm defining L tilde of f of z to just be equal to 1 minus y of f of x. So I'm not doing the projection onto the positive component. And we're going to define L this composition in the same way, right, in the exact same way. Okay, so first thing to notice is that if I look at h of z, which is just plus acting on z, this satisfies h of 0 equal to 0, and furthermore, the Lipschitz constant of h is just equal to 1, right? It's just linear or 0. Okay, so by Ledoux-Talleyrand, I immediately have that this is less than or equal to twice times two times the Lipschitz constant, which is 1, times the Rademacher complexity of this simpler thing to deal with. Okay, right, so that's one thing that we need to deal with. And now we need to worry about bounding this thing. And so to do that, we need to fix a function class f. So let's do that. We're going to consider the function class f of linear classifiers with bounded norms. So we're going to let f of x just be equal to w transpose x, such that the 2 norm of w is less than or equal to capital W. And we're also going to assume that all of the x's that I see are also bounded, almost surely. Okay, so, and now this is the set of steps that we're going to do over and over again, which is step 1 is bound, we need to bound BL. Right? And that's not too hard. That's equal to, if you remember, the supremum over, in this case, it'll be x less than or equal to bx, y in plus or minus 1, for example, and f in f, which corresponds to basically a w less than or equal to w of 1 minus y fx. And this is just equal, this is less than or equal to, actually this is equal to, you can achieve it, 1 plus supremum of x less than or equal to bx, and w is bounded, w transpose x, but we know that by Cauchy-Schwarz, this is just equal to 1 plus bx w. Right? So our bound scales with the how big my x can get and how big my my classifier's norm can be. Right. So that's usually the easy step. And the harder step is we need to bound the Rademacher complexity of f itself. And to do that, there are lots of different methods. For this one, because we have a simple enough function class, we can just go straight from the definition. So I have my Rademacher complexity, and I can pull the 1 over n out. That's the expected value over my data and my Rademacher variables. In this case, this becomes the supremum over w bounded of somewhere I equal 1 to n, sigma I w transpose xi. Right, so I'm just writing out the definition. So we'll notice that the w here is independent of I, so I can pull that out in the following way. Right, so far so good. I just factored that out. But we know how to now solve this inner maximization, this inner supremum, just by Cauchy-Schwarz. So we end up with this is actually equal to w over n, the expected value over my data and my Rademacher variables of sum or I equal 1 to n of sigma I xi. And I'm being a little sloppy, but these are all two norms. Okay, so now we need to deal with this. And the way to deal with this is what we want to do is really want to pull the expectation inside of this norm, because then nice things will happen. So we'll do it in the following way. The first thing is we'll expand out the definition of this norm. And if you kind of just write it out in the appropriate way, you see that this ends up being equal to the sum over I and j of sigma I, sigma j, xi transpose xj. Okay, well now the nice thing is that we know that the square root of z is a concave function. So by Jensen, I can pull the expectation inside. But the nice thing here is that the sigma i's are IID, so the only ones that end up the only things that end up staying are the cases where I is equal to j. So this is equal to then the square root of the expected value over s and sigma I of sum over I equal 1 to n sigma I squared xi squared. Right. Sigma I squared, this is always equal to 1. Right? It's just the square of plus or minus 1. And so I can further bound the xi's. I know that they're all less than or equal to bx squared. And ultimately what we end up with is this is n times bx squared under a square root. So this is exactly equal to a w over square root n times bx. And we see very, very clearly here that the norm of w, how big w is allowed to be, is with capturing the expressivity of our linear classifier. So if we put this all together, kind of putting everything together, we see that with probability at least 1 minus delta over s over my training data, and for all f in my function class f, I have that, I can write out that the delta gen of f, which is the difference between the true and empirical risk, is less than or equal to, I end up with 4bx over square root n. That's my Rademacher complexity term, plus 1 plus bxw square root log 1 over delta over n, which up to leading factors, we're seeing that this scales as bxw over square root n, and I'm suppressing the logs there. Right, so this really, again, makes clear w is a measure of the complexity of the function class f that we defined. Okay, awesome. So that's our whirlwind tour of the basic ideas from statistical learning theory that we're going to now, in the second half, build on by connecting them up to the underlying stability properties of a dynamical system. And just as a little bit of a hint, you can imagine that if your x's are being generated by a dynamical system, then the underlying stability properties will manifest themselves in this supremum here, as well as this expression here, because you're going to have these x's that are popping up. And so we're going to want to connect the stability guarantees of my underlying dynamical system to these corresponding bounds in Rademacher complexity. All right, so why don't we take about a 10-minute break? Is that okay? Or sorry, I think you're muted. What's the appropriate length of a break?
I think it's okay, 10 minutes, maybe until
okay.
until 4. It will be 4:10 over here. So
yeah. So why don't we meet at 10 past the hour?
Yeah, that's perfect.
Right, but maybe before we go on break, I can also just pause quickly and see if there are any questions. Okay, well, if there's no questions, either I'm doing a really good job of explaining this clearly, or I've lost all of you. So I'm hoping it's the first one. But you know, don't be shy. Like I said, if there are any questions, interrupt and go ahead.
Yes, so I would have a question.
Yeah, absolutely.
So in the beginning, when you motivated like these generalization errors, right? You had these two examples with these two different regimes on how the generalization error decays, right? And one was the central limit theorem type thing that you get with the Höfting bound, which was this 1 over square root of n, and the other one was the faster one, if I remember, which was this 1 over n, right?
Yeah.
And so is this? So this kind of reminds me on, you know, like the second, like a large deviation type of regime where you're analyzing a different kind of regime, like further away, and therefore you can decay it faster. Is that correct insight, or what's the reasoning of these two different regimes you get?
Yeah. So in the one function example, it's kind of intuitive in the sense that, let me go back up here. The right way to think about it when you're just analyzing sorry for the scrolling. When you're just thinking about analyzing a single function class, right? The idea here is that if I have 0 empirical risk and I have bad true risk, then this means that I've essentially witnessed n1 minus epsilon probability events. So it's really the kind of probability that my data tricks me into thinking that I have a good classifier when I don't. So in that case, that's why it's a different analysis tool. I can really exploit the fact that I have 0 empirical risk to formulate it in this way. Now, in the more general setting, and Stephen's going to talk about this a little bit more this afternoon. I wasn't planning on going over the derivations for the fast rate regime. What you actually end up doing is rather than analyzing things in the kind of large deviation setting, you use a tool which is known as a local Rademacher complexity, which is so here we're analyzing the Rademacher complexity, and we're looking at all function classes H, and we're doing uniform convergence. The way you get fast rates out of these things is you use a notion of local Rademacher complexity, which is you restrict your attention of proving this uniform convergence only to a subset of functions that achieve a low empirical risk. So you would only consider the set of H, you know, my function class, and there'd be an additional constraint which would say that the empirical risk achieved, or the true risk achieved by my function is less than or equal to some bound. So it's actually a more local, fine-grained analysis, and you're able to do this in both cases by exploiting the fact that you know that your empirical risk will be small. So it makes sense to look locally. Does that make sense?
Yeah, this is super interesting. Yeah, thanks a lot for sharing the intuition.
Yeah, of course.
then like, okay, if nobody else has a question, I would have a second one, yeah, which is a very like maybe, you know, like kind of vague question, but you had like these theories for the generalization that you listed in the beginning with, you know, starting with algorithmic stability, then uniform convergence, etc., etc. And I was wondering, so you said like, okay, when you dive into uniform convergence, so you know, like the complexity of the function class kind of gives or determines the generalization properties. Now, so in practice, many people also use this type of regularizer to the kind of, you know, like empirical risk minimization problem. So where does this fit in, the idea of adding a regularizer? Because it's also a notion that can improve your generalization, or is that only like?
No, that's a great question. And let's look at the linear classifier as a specific example, because I think this makes it pretty clear. Right. So in practice, you're typically not going to actually enforce this bound. Instead, in practice, what you'll do is you'll promote small w's by adding a suitable regularizer. But you know, up to duality, roughly speaking, whether I have an explicit constraint or a regularized penalty, they're kind of the same thing. There's just so that's kind of the intuition here. This is exactly that. This is saying that you want to regularize W and make it kind of trade off between how large you're allowing W to be and what your empirical risk looks like. So that's exactly the right intuition.
I see.
Yeah.
Okay, thanks a lot.
Awesome. Yeah, no, those are great questions. Thank you. So let's take a quick break and I'll be back at 10 past the hour.
Great. Thank you so much.